So here we've got a wave function like we've been talking about. It's a sum of any number of waves. It might be the sum of two waves, it might be the sum of more waves. And as a reminder, the wave itself is the purple one. We call that the oscillating term, that's the wave. And the envelope is the red. And that shows the packet, the wave packet. This is called a wave packet. It's one of the humps, one of the lumps, one of the pieces of the envelope, right? But one of the things that you can notice is that the wave packet, I'm trying to find another color to draw in, the wave packet is taken up by half of an envelope, right? So that's half a wavelength of the envelope, right? That's half a wavelength of the envelope because the other half of that wavelength is over here. So we can talk about the wave packet that is part of this wave. And, we have already talked about the fact that we can later on generalize and say, we can create sums of waves, which are wave functions. Again, this is just an arbitrary wave function, which turn out that can have, one wave packet and a single wave packet, right, which is the box in blue, and it goes to 0 on either end just by summing up enough single frequency waves. Whoops, hold on. So we can just sum up single frequency waves and 2 waves, 3 waves, 4 waves, 5 waves, whatever, and we can, isolate a single wave packet. But regardless of whether we're talking about 2 waves and then we have, a bunch of wave packets next to each other, or whether we're talking about an infinite sum of waves and we're talking about a single wave packet, we can talk about the localization of the wave packet. The localization of the wave packet is simply that, delta x. That's the localization of the wave packet. How much space does it take up? The wave packet, the single, half wavelength of an envelope. How much space does that take up? So it really is. It's just it's half the wavelength of the envelope. Okay, so if the envelope term is, right, the envelope term, doesn't matter if it's sine or cosine again, I will stop explaining that. The envelope term is delta k over 2 times x minus delta omega over 2 times t. That's the envelope term. Sorry, don't remember if I said. So what's in green at the bottom, that's the envelope term. And the wave number of the envelope term is delta k over 2. And wave number, delta k over 2, is 2 pi over lambda. So therefore, lambda is equal to 4 pi over delta k, 4 pi over delta k, and so therefore lambda over 2 is equal to 2 pi over delta k. And remember, lambda over 2 is just delta x. That's the localization. So therefore, we get delta x, delta k equals 2 pi. So the localized region of this wave, that wave packet in the middle there, any one of these wave packets, takes up an amount of space, in one-dimensional space, it takes up this much space, 2 pi over delta k, which also leads to, again, this relationship here, which might look familiar to you as something which is similar to what's called Heisenberg's uncertainty principle. Let me come back to Heisenberg's uncertainty principle in a second, but let's just think about what this means as far as localization, right? This idea of localization. This says that delta x is how localized the wave packet is. Delta x is how localized the wave packet is. And if delta x times delta k is equal to a constant, right? 2 pi is just a constant, then we can localize a wave packet better. We can make delta x smaller. Delta x gets smaller if delta k gets bigger. Right? So it's how well do we know delta x? How well do we know how localized? How well do we know? That might not make sense, but how localized is the wave packet? The wave packet is going to be more localized if I have more spread in k's. In other words, I know delta x better if I know delta k worse. Or if I have less of a spread in delta k, I know delta k better, then I know delta x worse, right? So if delta k goes down, then delta x goes up. This is this concept that we see in Heisenberg's uncertainty principle. If you don't know what Heisenberg's uncertainty principle is, certainly you've heard the jokes that you can't both know how fast you're going and where you are at the same time. You can only know one or the other, and that's this relationship. That's what this relationship is. And what we will see later is that this wave number k, remember k is just defined as 2 pi over lambda, but this wave number k is like momentum. We will see that it is like momentum, it's proportional to momentum. So what this localization relationship tells us for wave packets is that delta x, delta p is equal to a constant. What that tells us, right, whatever the constant is, because p is different than k, whatever that tells us, it tells us that we can only know either delta x or delta p so well. If we know one better, we know the other worse. In other words, my location is delta x and my velocity is given by delta p. And so if I don't know if I know my location really well, I don't know how fast I'm going. If I know my speed really well, then I don't know where I am. And that really is sort of what that's saying. Heisenberg's uncertainty principle. So this is pretty much Heisenberg's uncertainty principle. What Heisenberg's uncertainty principle actually says is that delta x, delta p is greater than or equal to some minimum constant, which is non-zero, right? Some minimum non-zero constant. That's what Heisenberg was able to show. He was able to show that for any wave function, not just this, not just this particular wave function right here, but for any wave function, what Heisenberg was able to show is that delta x, delta p is greater than or equal to a constant, which is not zero. And that tells us that we can't know both our momentum and our position exactly at the same time. We can only know, if we know one exactly, we don't know the other. If we know one exactly, we don't know the other. That's what Heisenberg's uncertainty principle is. And just as an aside, we can also look at the time dependence. The time dependence, remember that the envelope term was cosine delta k over 2, x minus delta omega over 2t. So by the same argument, since the distance the distance in time that it takes one half of a wave packet, the distance in time that it takes one wave packet to pass you, that's the amount of time that it takes half the wave to pass you, is half the period. So what that tells you is that delta omega over 2, which equals 2 pi over the period of this wave function, therefore, hold on. Sorry, brain blip. So that means the period is 4 pi over delta omega, for this wave packet. And so the amount of time that it takes for half the wave packet to pass you by is period over 2, which is 2 pi over delta omega. So therefore, delta omega delta t is equal to 2 pi. So that tells you about localization of time and frequency. And frequency, we will see later, just like up here, wave number was like momentum. Frequency is like energy. So you can either know the location, you can either know when it arrived or what its energy is, but you can't know both exactly. You can either know when it arrived or what its energy is, but you can't know both exactly. That's also Heisenberg's uncertainty relationship. And again, while we figured out this particular wave packet was equal to 2 pi, it's some constant smaller than 2 pi, but there's a minimum constant that delta omega and delta t is equal to. And again, I will just remind you that omega, which is 2 pi over period, we will see later is like energy of a wave. Just like k is like momentum. That's just something we haven't shown you yet. This is Heisenberg's uncertainty relationship that has to do with localization. Localization in space and localization in time. So just about any example we can do is really just a plug-in, but let's just say we've got two single frequency waves. We're trying to tune it. Oh, and this is beats, by the way, is the way that I learned about beats was in tuning a piano. When you tune a piano, you can play a note on a piano and you can play a note on a tuning fork that you assume is correct. And you play them both at the same time and you listen for, if you expect them to be the same, you should hear no beats. But if they're slightly different frequencies, then you're going to hear beats. And so what you want is for the beats to get longer and longer and longer, the beat to get longer until the beat goes away. And by longer, we really mean a longer wavelength. And it ends up therefore being a longer wavelength. It's a lower tone. So a lower beat frequency. So let's just give the example of, I just chose two arbitrary waves. I don't know if, I'm not getting any units here or anything, so let's just pretend they're sound waves, and one wave has k and omega of 3, and one wave has k and omega of 6. And again, when we're talking about beats, we're usually talking about waves that have the same wave speed. So these do have the same wave speed, right? These both have wave speed of 1. Omega 1 over k1 equals 1. So how long does it take a beat to occur? All I'm asking really here is how localized is the wave packet. When you sum these two, how localized is the wave packet? That's what we're really asking. And so it really is just a plug-in to delta omega delta t equals 2 pi, and how long it takes is how localized it is in time. How localized it is in time. Delta t equals 2 pi over delta omega. So therefore, it's localized in time by 2 pi over delta omega, which is 3. Now, let's just say they're MKS units, that these are in radians per second or hertz, so that we end up with seconds. This is going to give us units of seconds. Right. Oh, by the way, delta omega is 6 radians per second minus 3 radians per second. And the 2 pi is actually 2 pi radians. Not that it matters, because radian is a unitless quantity. And so that ends up giving us 2 pi over 3 seconds, which is about, 2 pi over 3 is about 6.24, about 2.08 seconds. So this has the beats pass by every 2.08 seconds. So you hear mom, 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 mom. That's your beat. I know you enjoyed that sound effect that I was making.